Hey everyone, we are going ahead and going through section 1.4, solving linear systems, honors algebra 2. We are on page 18 in your math journal. I'm just going to walk you through a couple things here. The review, this is solving systems with using two variables. So this should all be review from algebra 1. If you feel like you need additional time spent on this, you can email me, you can feel to do extra problems from the book or that are online and so forth. I'm just not going to spend a ton of time going over a system with two equations as we're going to get into a system with three equations today. All right, so just as kind of a recap real quick, we have a system is, basically means two or more equations. When we're asked to solve a system, what we're asking for is basically we're saying, where do they intersect? So if this equation, when they intersect, it's called a solution, and that solution is a point. And so when we solve this algebraically, if you remember using like elimination or if we use substitution, you would find an x value and then find a y value because you're finding the x and y value of the point where they intersect. And so if you remember doing this from algebra 1, we had three kind of scenarios when we talked about the number of solutions for systems. We had an infinitely many solutions. So infinite number of solutions, and that was basically where you had two equations that they were the exact same equation. One equation might have been like a scalar multiple of the other one. A good example is this option up here, number C. See how like if I multiplied this by -2, I would get from here 2 times -2 is -4, 3 times -2, and then 3 times -2. If I just scaled this whole equation up by -2, I would come to that whole equation, which means if you graph them, they're the exact same equation. So imagine you have two lines, they're exactly the same, and how many times do they intersect? Well, they intersect infinitely many times because they're on top of each other. And so that's why you have infinite number of solutions. Algebraically, what will happen is if you solve this algebraically, so graphically you'll see two lines like kind of on top of each other. If you look at the equations, you will see one is a multiple of the other. But a lot of times algebraically what would happen, and I'm not going to solve this one, but you might get something like 0 equals 0, like if you were solving this. And so what this means is in an infinite number of solutions, you will get a true statement. And what that means is like it would make sense. Like it wouldn't say something like 0 equals 5. Obviously, that doesn't make a whole lot of sense. And so if it's infinite number of solutions, you're going to have a true statement. So 0 equals 0, 10 equals 10, -1 equals -1. Whatever the case may be, it's going to be a true statement. The next scenario we have is where there are no solutions. So no solutions implies that you have two linear equations that basically never intersect. What are they called? They're called parallel. So no solutions means that you have two parallel lines. Obviously, graphically, they're going to look like they're parallel lines. Algebraically, what's going to happen is you're going to have a false statement. And so what that means is algebraically, when you go to solve it, you'll get something like, 10 equals 0, for example. Obviously, this is a false statement. That's not true. And that's how you can kind of tell algebraically that result is having two lines that are parallel. In other words, they're never going to intersect. They're not going to have any solutions. You can't find a value for that. Most typically, when you have two linear equations, they are going to intersect. Because they're both straight lines, they're going to intersect in one point. This point is called your solution, and it's your x value and your y value. So in most cases, you're going to find one solution. However, there can be scenarios in which you'd have no solutions or infinitely number of solutions. Real quick, again, just kind of reminding yourself about how to do elimination and substitution. I was going to show you some examples here. Elimination basically just means that you are multiplying one equation by, like you're scaling it up. So for example, I'm going to take example C here. If I wanted to, let's say, get rid of my y values. So elimination means you're either eliminating your x's or eliminating your y's. So if I'm going to add these two equations together, I want to get rid of my y's. Well, before I do that, I'm going to multiply this whole equation by -2. And the reason I picked -2 is because if I look at my values, if I multiply -2 times y, I get -2y. And that means if I have -2y and +2y, they'll cancel each other out. And so what would happen is I would have -2x minus 2y equals 0, and then I'd have 3x plus 2y equals 1. So the equation, I didn't have to multiply by anything, so I didn't change that one at all. Now that I can go ahead and I scaled this one up, see my y's would cancel, and I would solve my equation, x equals 1. Remember that you're not done once you solve for x, you have to plug it back in and solve for your y value. So then you'd pick either one of your equations. So it looks like the first one would probably be the easiest. And if x is 1, I'm just going to put in 1 plus y equals 0, which means y has to equal negative 1. So the point of intersection would be the point 1 comma negative 1. Substitution is the other kind of other option you can use here. And that's where a lot of times you use it if you have just a variable, there's no coefficient in front of it. So like for example, on this one I might say I'm going to solve my equation for x. In other words, I'm going to add y to both sides. And so I reworked this equation and I just solved this equation for x. So I added y to both sides. So then what you do is you substitute into the other equation. Since x equals 1 plus y, I'm going to substitute in for x, substitute 1 plus y. So it's going to look like this. 2 times 1 plus y equals 5. And what that does is it gives me an equation with only y's, which then I can ultimately solve. I can solve for y. Once I know what y is, I can plug that back in and solve for x. So that's how you solve a system, how you probably did in Algebra 1. You probably remember this. Now let's get into some fun stuff where we're solving systems that involve 3 equations. So I'll just show you this example down here. See how you have x, y, and z. So we have a third dimension to our graph. And if you kind of graph your x and y axis and imagine that there's like 3-dimensional, that this is kind of coming out at you, there's another axis called our z-axis. And so what we have here is we have an equation that has 3 different variables. A lot of times we use, we can use our graphing calculator for this, but we can also use something called matrices to help us solve systems that are this big. Today we're going to concentrate on just doing some algebra because, we like algebra and it's fun. So I'm going to show you how to do that algebraically, but probably as you move forward in mathematics, you'll be using like matrices and stuff to solve systems that get this complicated. But for now, it'll be fun to kind of practice our algebra skills and see how well we can do with those. Okay. So a couple things just to kind of walk over. Linear equations in 3 variables. That's just what I was showing you on the other side. It means linear equations means there's no x squared. It's not being, it's not square root or cube root or anything like that. A system of 3 linear equations implies that you are graphing the 3 on the same grid, which means that you are going to be looking for where all 3 of those lines intersect. Again, you can have, there's only one real solution to a system of linear equations because the lines don't bend, so there's only one point in which all 3 lines would intersect, and that's going to be your solution. How you write your solution would be a little bit different. Instead of just x and y, you'd have to write it as x, y, and z. So the solution of linear systems is the point in which all 3 lines intersect. I'm going to kind of skip through some of this. This is like basically some of the notes, like here's what you do step by step. I think it's easier just to kind of walk through a couple examples. And so, and then explain as we go. All right, you're going to probably need another sheet of paper. And so if you want to pause the video to grab that, just because there's a lot of algebra and it takes up a lot of room. So if I'm going to grab another sheet of paper, I'm not going to do all these problems, otherwise we'd be here all day. I'm not going to expect you to do, tons of this on your own, just because they are kind of labor intensive. I'm going to do 2 problems and then go over a couple special scenarios with you. So we're going to do number 1 and we're going to do number 6. So here we go. I'm going to grab a sheet of paper and I'm going to look at these 3 equations. So my first one, I have x plus 2y minus 3z equals 11, 2x plus y minus 2z equals 9, and 4x plus 3y plus z equals 16. All right, so your first goal is you pick 2 equations and decide which variable it is that you want to get rid of. So for example, I'm going to decide, and again, there's not really necessarily a right and wrong way to start this. I'm going to pick the top 2 equations, so I'm going to ignore that third one, and I want to get rid of my x's. So if I'm just looking at those top 2 equations, move this, and I just want to get rid of my x's, if I can multiply, I'm going to use the elimination strategy here. If I can multiply that top equation by -2, then my x's would cancel out because I'd have -2x and +2x, and therefore they'd go away. So that's what I'm going to do. I'm going to go ahead and multiply that top equation by -2. So I have -2x minus 4y plus 6z equals -22. Be careful here because you mess up on a multiplication or a sign, it throws everything off. So just be careful. And then the second equation, I don't need to do anything to it because it allows me to cancel out my x's. So I'm just going to rewrite it over here. All right. Now that I multiplied that equation by -2, I'm going to go ahead and add them together. So again, what you'll notice is that your x's cancel out. You will get -4y and y gives me -3y. And then 6z and -2z is +4z. And then -22 and 9 is -13. So I'm just going to kind of hold on to this equation here. I'm not going to do anything with it right yet. And now we're going to move on to another equation. So now what I'm going to do is I have to use one of the other equations. So I have to use this equation and then one of the two I used from before. So I'm going to take these two equations and put them together. So now I'm going to take basically equation number 2 and equation number 3. I'm going to do the exact same strategy. You want to get rid of the same exact variable. So I got rid of x's the first time I did this. Let's get rid of x's now. So in order for me to get rid of my x's using these two equations, I'm going to multiply this top equation, the middle one actually, by -2. And again, why I do that is so that my x's cancel out, because that would give me -4, this would give me +4. So I'm going to do the work over here. So I'm going to multiply that first equation by -2. So I get -4x minus y +4z equals -18. And then the second equation didn't have to be changed. There could be times when you'd multiply one equation by one number and another equation by another number, but we don't have to worry about that right now. All right, so now I can add those two things together. My x's would cancel. I'm going to get y plus 5z equals -2. Great. All right, we're getting there. Now what you're going to do is you have a system. This is something that we're somewhat familiar with because this is what we just did. Now we're going to solve the system using these two equations. So I have my, I have -3y and 4z and equals -13. And I have y and 5z equals -2. So I'm going to go ahead and I'm just going to rewrite them just for fun, just so that they're all kind of in the same spot. So -3y plus 4z equals -13. And y plus 5z equals -2. All right, you need to decide on either you can use substitution or elimination. If you haven't already noticed, I like elimination just because I find it to be easier. I'm going to go ahead and multiply this equation. I'm going to get rid of my y's. I'm going to multiply this equation by 3. And if I do that, that way my y's would cancel. So the top equation right now is not going to change. And then this becomes 3y plus 15z equals -6. All right, add them together. Those would cancel. I get 19z equals -19. Divide both sides. I get z to equal -1. Remember your goal. Your goal is to find x, y, and z. Well, you just accomplished 1/3 of your goal. So now we're going to go ahead and now that we know z, I can plug it back into either one of these two equations, so either this one or this one, and solve for y. So I'm going to take this bottom equation, so y plus 5z equals -2, and I'm going to plug in -1 in for z. So that basically causes it to become -5 here. And then I'm going to solve for y. And so I get y to equal 3. And then last but not least, now that I know z and I know y, I can go all the way back up to one of my original equations. I'll just take the first one. So it's x plus 2y minus 3z equals 11. I'm just going to rewrite it down here. Now I'm going to plug in 3 for y and -1 in for z, and I'm going to solve for x. So if I plug in 3 for y, I get, this is +6. If I plug in -1 here, I get +3. So x plus 9 equals 11, x equals 2. I've solved my equation algebraically. A lot of times I write my answer, x, y, z, as an ordered pair, just to kind of reiterate the point that we're in a system, which ultimately means we're solving for a point where all three of those lines intersect. So as you can tell, obviously it takes a lot of math here, a lot of work, but a little fun, right? We had a little fun with that one. I like it. I like doing some algebra. So that was kind of a fun one. Let's do another one. I'm going to grab another sheet of paper. We are going to do number 6 on this one. Just to kind of, if you don't feel like you need another example, feel free to skip ahead in the video. This is for anyone who would like me to see me work out one more. I would imagine you've already solved equations in 2 variables. I can't imagine that you have been taught 3. So this is generally going to be a new concept for most of you. All right, so I just rewrote number 6 here just so that I have it, kind of in one spot. All right, so what we're going to do is I am going to go ahead and solve this equation. I'm going to try to use, what did I do here? I think I'm going to try to use, substitution on this one. Yeah, I can use substitution on this one. Okay, so I just want to show you some other options. Like there's not just one way of doing this. And so I'm going to go ahead and solve this equation by using substitution. So I'm going to go ahead and solve. I'm going to start by taking, again, what I look for is like a variable by itself. So I'm going to use this equation here, and I'm going to solve it for x. So I get x to equal, if I move the 2y and I move the 5z over, I get negative 2y plus 5z minus 12. So all I did there was just solve that equation for x. And now what I'm going to do is I'm going to substitute it into my other 2 equations. So this is just using the substitution method. So now I'm going to take this equation right here, and now I'm going to substitute in all of this in place of x. So it would look like this. 2 times negative 2y plus 5z minus 12 plus 2y minus 3z equals negative 2. All right, so the only thing I'm really doing here is just kind of distributing and combining like terms. So I get negative 4y plus 10z minus 24. So I can put my y's together, so I get negative 4 and positive 2 gives me negative 2y. I can put my z's together and get positive 7. And then I'm going to put all my numbers on the other side of the equation. So I'm going to add 24 to both sides. And so I'm going to get 22 on that side. So I'm good to go here. Next, I'm going to go ahead and plug in, so I'll just kind of do this to kind of separate it. Now I'm going to use my other equation, and I'm going to substitute in, so now I'm going to plug this x into this equation over here. So, So I'm going to take the x that I originally solved for and plug it into this equation right here. I'm going to do the same kind of deal. So 3 times negative 2y plus 5z minus 12 minus 4y minus z equals 11. Okay, so I'm just kind of doing the math here, just distributing, and I'm going to combine some like terms. Negative 6 and negative 4 gives me negative 10. Negative 1 and positive 15 is positive 14. And I'm going to add 36 to both sides, so I get, what is that, 47. All right, so now I have 2 equations, and now I'm going to solve it like I've done in the past with just kind of using elimination or substitution. So I'm going to take my 2 equations, so negative 2y plus 7z equals 22, negative 10y plus 14z equals 47. And now you get to decide on, whether or not you want to, how you want to go about doing this. If you want to go ahead and use substitution, or if you want to use elimination. I'm going to use elimination because none of my variables here, they all have coefficients, and I don't like using substitution because you get into fractions and stuff. So I'm going to go ahead and just use elimination. You can solve for your y's or solve for your z's. I'm going to go ahead and get rid of my z's. So I'm going to take this top equation and multiply it by -2. And again, why I do that is so that this becomes -14, and then if I add it to +14, they would cancel out. So -2 times -2 is positive 4y, gives me -14z equals -44. And then -10y plus 14z equals 47. All right, obviously these cancel. Over here I get -6y equals 3, and y is going to equal -1/2. It is okay to get a fraction, just you didn't do anything wrong necessarily if you have a fraction. So I get -1/2 as my answer. All right, so now remember we are going to go back and now solve for z, and we're going to solve for x. So I'm going to go back to one of these equations. I'll use this one right here. I'm going to plug in -1/2. So -2 times -1/2 plus 7z equals 22. I'm just going to solve for z. So negative times negative is a positive. 2 times 1/2 is 1. Subtract 1, divide by 7. And I'm off the screen here. I get z to equal 3. So I just went ahead and plugged in -1/2 into this top equation and solve for z. Run out of room here a little bit, but I'm going to go back up all the way to the top, and now I'm going to solve for x. So I'm going to go back up to my original equations. I'm actually going to use this one because I figured it's already solved for x, and I'm just going to plug in already my numbers that I know. So I know y is -1/2, so -2 times -1/2, and I know z I got to be 3. So I'm going to plug all that in. So that gives me 1 plus 15 minus 12. So that's 16 minus 12, which ends up with 4. So my x value ended up being 4, my y value was -1/2, and my z value was 3. All right, well, that was a lot of fun. So that was your example of solving a system with 3 linear equations. I want to walk through 2 more scenarios just to kind of give you guys all the options here, because I don't want you to come across some problems later and be like, well, we never went over that. So I'm going to make some up. So if you want to grab a paper or follow along. And I'm going to walk you through a couple examples of problems that I feel would be helpful for you. All right, so the first one is going to be a no solution. We talked about what no solutions look like if you have just 2 equations. I want to show you what no solutions would look like if you have 3. So if I give you this system, so something basic, x plus y plus z equals 2, 5x plus 5y plus 5z equals 3. And the last one is 4x plus y minus 3z equals -6. All right, so what I'm going to do is I'm going to go ahead and take the top 2 equations. I'm going to start this way the same way I would any other problem with 3 systems, because you don't know that it doesn't have any solutions. I'm telling you that it doesn't, but if this were on a test or something, you wouldn't know. I'm going to take those 2 equations and I'm going to go ahead and solve it. So I'm going to multiply this top equation by -5, just so I can get rid of my x's. You might also realize that you can get rid of your y's and your z's here, which is, again, why we get this to be no solution. So anyway, what would look like is -5x minus 5y minus 5z equals -10. And if I added it to the second equation there, you will notice something. When I go to add these, x's, y's, and z's cancel out. They give me 0. So again, we're talking about numbers here. And this is -7. So why does this give me no solution? Because this is a false statement. And anytime you get a false statement, it results in no solutions. So that's what I want to make sure you understand. Again, kind of same kind of process as we did when we were solving that other one, when we had 2. Let me go one more example and then I'll let you guys go. Obviously, we haven't talked about the one that's infinitely many solutions. You can call it infinite or you can call it many solutions. I don't care which. Let me give you a system to solve. So let's go with the x minus y plus z equals -3. X minus y minus z equals -3. And 5x minus 5y plus z equals -15. All right, so you might already notice from looking at this one, again, you don't know that it's not necessarily a many solutions one, but if I go to solve this, I'm gonna take these top two equations, for example. They're already kind of set up. My z is plus, I already have a plus z and a minus z. So if I added those together as is, the z's would come up. So I'm gonna go ahead and start there. So if I took those two equations, and I didn't have to add, I didn't have to scale them up or anything, but my z's would cancel. So I get 2x minus 2y equals -6. So I got this equation. And so far it looks good. I'm like, okay, well, things are going well, right? I'm going to go ahead and take the second two equations, so these two. Remember, I need to get rid of my z's because, again, I have to get rid of the same variable. So on these two, again, my z's are already kind of set up. So I have x minus y minus z equals -3, 5x minus 5y plus z equals -15. If I go ahead and solve them, I get 6x minus 6y, z's would cancel, and I get -18. All right, now I have two equations. Let's go ahead and solve this system. So I want to go ahead and either get rid of x's or y's here. I'm going to go ahead and multiply this equation by -3. The reason why is because if I multiply this by -3, I can get rid of my x's. So this becomes -6x plus 6y, negative times negative, equals +18. And this one is 6x minus 6y equals -18. And then look what happens when I go to add them together. So I scaled this up by -3. This cancels, and this cancels. So what we notice here is I get 0 equals 0. This is a true statement, which means I have many or infinite solutions. So that's how it would look algebraically if you were solving a system with 3 equations and you were solving it algebraically and you got something that was infinite number of solutions. Again, same kind of deal. You're going to end up with a true statement as opposed to when you have no solutions and you get that false statement. Okay, that should be enough for now. I encourage you to practice. If you have questions, obviously take notes and write down your questions, and feel free to email me, or obviously we'll be going over this in class the next day. All right, bye guys.